All right, well, yeah, so getting back to what I was saying, on Tuesday we talked about kind of fitting univariate time series models in Stan, primarily using this package that we had assembled for kind of bundling a lot of those univariate scripts in Stan, so you don't have to start with those yourself. Today I'm going to be talking about fitting multivariate Bayesian time series models, and we'll be it became a headache to kind of jam in a lot of these different, once you're like developing R packages, it gets pretty unwieldy once you start throwing a lot of different Stan scripts in the same package, especially if they're different kinds of models. And so it just became easier to have things a little bit separate, which makes it more demanding for you because you'll have to install a few more of these packages. But essentially what we've done is bundled a series of these functions and models for fitting like the DFA type models that Mark was talking about a couple weeks ago. And then a second package for fitting what we think about as kind of MARSS models, or these multivariate time series models where we have time series are mapped to individual underlying states. And so we'll talk about both of those today, in addition to a few other topics. So for starters, I actually wanted to to just kind of push pause on the Bayesian estimation. I think that Stan is super powerful for doing MCMC very efficiently, and we talked about that a little bit on Tuesday. But for really complicated models with thousands of parameters, for example, or some of these giant spatial models, it becomes too much to be able to diagnose potential problems in your code or your model when you have to essentially run an MCMC chain until you get your model to converge. So thousands of iterations, and then pretty soon you're waiting like a half an hour to get feedback every time you want to tweak something with your model or change your prior. So Stan unfortunately has this other type of estimation that's kind of built in, and it's not as widely used as MCMC for sure, but I think it's increasing in popularity. And it's just called map estimation. And so that's what we're going to be starting with first. So map stands for the maximum a posteriori estimation, which is, it's basically like we do maximum likelihood. We find the peak of a likelihood surface. We can do the same thing in Stan using the maximum posterior distribution. The two differences, well, the one major difference is that unlike the maximum likelihood, which doesn't involve the prior at all, to generate that posterior distribution, we need to include the prior. So if you're going to do this map estimation, you have to realize that any of the estimates you get may be somewhat conditional on your choice of prior. So it's probably worth, if you actually use it for papers or analyses, it's worth kind of doing some sensitivity to that. So the map will generate a point estimate of your unknown parameters in a model. There's a few different optimization algorithms available, and if you're a user of functions like optim in R to generate maximum likelihood estimates, these should be familiar. There are things like the BFGS algorithm, the Newton algorithm, etc. And as I said before, this is a very quick check for model convergence and whether you might have a model that's misspecified, rather than the model taking 30 minutes to run. For a big model, it'll take less than a minute. So it's very fast. It's a good diagnostic. So one of the tools to make this a little bit more accessible in the time series type models that we're using for this class is essentially, put a flag into this. We were talking about this fit Stan function that will just call one of our underlying Stan scripts after passing in some data. And one of the things we've done is this is kind of essentially the syntax for fitting a DLM using that package, where we just specify the name of the model and the data. But if we want to do the map estimation instead of the MCMC, essentially I've just put a flag in there, and all the flag does is if the map estimation is set to true, it'll generate that maximum posterior estimate. If it's set to false, it'll do MCMC. Okay, so the good news is that map estimation is super fast. The downside is that when you look at what is returned, it's kind of a mess. And so the map estimation will give you, or the optimization that's called on the stand model will generate kind of a list of parameters, including both what we think about conventionally as parameters. They're unknowns that we have to assign prior distributions to. It'll also, though, generate estimates for all the underlying states in a time series type model, all of the variances, et cetera. And so anything that's not just a parameter but a derived function of a parameter is going to get returned, meaning we have to figure out how to sort through this an ungodly amount of output here. So there's a number of different ways to do that we'll talk about. The list object that gets returned also has a return code, and so I think if you're using Optim, you also know that if you're working on a maximum likelihood problem that gets trapped easily in local minima or maxima, one of the ways you can look at convergence or assess convergence is whether whether you have a value of 0 that gets returned. Usually Optim will return different numbers are associated with different codes, but the value of 0 means everything's good. So I think same thing goes here, where we want to look for this return code of 0. It will return the maximum posterior value at that set of parameter convergence. So that is the third piece. And that's pretty much it. So getting back to what I was saying, we have a ton of output. If I go back, say 2 slides to this huge list, this contains both process deviations for this DLM type model in addition to the predictions. If all we care about is the predictions, though, we just need to take this giant list of parameters and find the names in the list that include pred, which we were using to store the predictions. So in this case, there's a number of functions that you can use to do kind of string matching in R. The grep function is pretty powerful, but we can just find the names of the parameters that get returned in that map object, pull them out, and then make some plots. So for a slide, why is it not going? Oops, why is that? Oops, I had the same slide twice. Okay, so there's a couple options that we might want to turn on or off. As I said, the map estimation is a part of this. If we do map estimation by itself, it doesn't return any parameter estimates or uncertainty around parameter estimates. It can generate standard errors, though, and so the way to do this is it can also try to estimate the Hessian matrix. And if you worked with Hessians before, you know that the Hessian is the inverse of the covariance matrix. So if we can return that, invert that Hessian matrix, pull out the diagonal of that, that will essentially be the variances of the parameters that we want to use to generate confidence intervals, for example. So just specifying. So again, the only other flag that we've included here is just to turn this Hessian estimation on or off. We can do that. We can also change the algorithm, and so I think there's not a lot of differences that are between these different approaches, other than I think that BFGS is considered to be conventionally slower than the default algorithm, but it's also sometimes more robust. So that's what that looks like. More importantly, how do these, the map estimation, as I said, contains the prior distribution or the prior and the posterior MCMC draws also contain that information. So we ideally would like to see them kind of line up. In this case, I wanted to take kind of our posterior means that were estimated for the DLM. This was the same code that I used on Tuesday, where we just do the MCMC to find kind of the squiggly line that best goes through this logit transformed salmon survival data. when we look at the map estimates falling on that, it falls exactly. So if I scroll back and forth, this was just the black line represents kind of the posterior mean. The blue line here represents just kind of the map estimate. They're exactly the same, which is really good. We want to see them agree. So that optimization gives an answer that's essentially at the posterior mean. So we got the same answer out in a fraction of the time, which is great. Okay. Okay, so for map estimation, we're going to come back to that a little bit, I think, towards the end of class when we kind of do some of these problems in kind of the lab portion. The second thing I kind of wanted to talk about was fitting multivariate time series models. And so multivariate time series models, everybody's familiar with that in this class. These are going to be models where these are essentially multivariate time series models that are not DFAs. So these are what we think about as kind of a MARSS type model where we have counts, say, of several species through time, and we're interested in whether or not they have a shared trend, or whether or not they are maybe mapped to the same population state, or whether they have variances that are equal or unequal. So those kinds of questions are the kinds that that I'm referring to here. And over the last few years, we've been developing this package that's on the repo for this class called TVARS. It's something you can install using DevTools. You don't need to do that now, and we're not going to be using this for the lab. So it's there if you would like to explore it, or use it later on in the class or for your project, etc. So so this function can do basically everything that the MARSS type function can do for these kinds of problems. So as I said before, are two species experiencing the same trend? Are the process variances equal or unequal? Are they correlated? Are the observation error variances equal or unequal or correlated? And then finally, whether the two species might not just experience the same trend, but be two replicate observations of the same state. So that's kind of all of the features that are available. The data matrix Y here is passed in the same way that we would pass it in MARSS, where we have time across the columns and the time series across the rows. One of the major advantages of using this package in a Bayesian framework is that we can switch up the observation error distribution really easily. So in this case, I think we've implemented a few count distributions like the Poisson and negative binomial, binomial distribution, and a few other kind of heavy-tailed positive distributions like a gamma or a log normal. So these are fairly easy to specify. It changes the meanings of some of the parameters a little bit, but for the most part, I think that it should be pretty straightforward if you're familiar with GLM and those kinds of packages. Okay, so we just to do those kinds of shared variance type models, we just have a series of arguments. I'm not going to dig into them or show really examples, but these are specified very similarly to how we would specify them using MARSS, where we have an argument for the shared R representing our observation error, an argument for the shared Q representing our process error variance, and those can be equal or unequal. One of the other features about this is that in addition, we can also think about the data being structured hierarchically, so we could have a kind of a complicated set of combinations of those R's and Q's. I forgot to include this in the argument list here, it looks like, but we have a process which is an indicator vector that essentially behaves exactly the same way as the Z matrix does in the model list in MARSS. And so again, this is for answering questions about how each time series that you observe is matched onto which underlying population state. So fairly straightforward. But I think probably one of the most interesting features, other than changing the families, one of the other things that we can do in a Bayesian setting is think about letting either the covariates or the autoregression coefficients act like DLMs and kind of wander through time as a random walk. And so what this means is that if you have a if you're in one species setting like a DLM, if you have an autoregression coefficient that is variable through time, what that means is that that's usually interpreted, for example, as the density dependence or the strength of density dependence of a population is the AR1 term. If that's autoregressive, then you're essentially letting the strength of density dependence is varying. It has a time varying component that isn't explained by your model. So that could be driven by changes in food availability or changes in competition from other populations, maybe other human disturbances. So all of the elements here that are autoregressive can be modeled as time varying. These can also include things like interactions between species as being time varying, which allows for a really powerful set of models to be fit. As kind of a word of caution, fitting these models with these time varying parameters are really data hungry, and so often you need to have not just one. You need to have more than one observation of the same species in each time step to actually fit these. So that's really to resolve kind of the trade-off that we've seen between observation variances and process variances. So the more data that we can feed into that problem, sometimes the more informative we can get the posteriors to be. So if you have data that's structured across multiple species and ideally multiple sites or multiple samples or surveys within a time step, these models might be the kind of thing that you can fit. Okay. Next, we wanted to kind of move on and transition to using kind of the Bayesian version of DFA. And this is something that has been, again, kind of cobbled together over the last 4 or 5 years. It's included a few different student projects for this class. And so I took a few of the pieces of code that we had in our ATSA package the last time we taught this class, bundled it with a few other pieces of DFA code from a few other projects that I've been working on, and just have it all kind of bundled together now. It's on this other repository, and again, you can just install it with dev tools. So the Bayesian DFA model is it can do everything that the MARSS version can, but there's some super interesting kind of identifiability problems. And so identifiability just means that whether or not we can actually estimate parameters and given the data. And I think that one of the best ways to demonstrate this is that when we have ideally we are doing Bayesian sampling using best practices, and that involves multiple MCMC chains that are initialized from different places. So we have multiple MCMC chains to work with. The other thing we know about DFA is that from what Mark was talking about, the direction of those DFA loadings and trends really don't have any meaning. And so you could have, you could fit a DFA in MARSS, and you could have a negative loading on a trend that's also negative, but when they get multiplied together, they give you a positive estimate of kind of population abundance, for example. So the absolute direction of those loadings and trends don't have any meaning. Okay, so what does that mean? Well, it means that if we are doing MCMC, and in this case, we have 3 MCMC chains, if I wanted to look at one of my loading parameters, for example, it will often look like this. And so we have 2 chains that have obviously converged kind of on the same answer. The third chain looks like it's converged on something totally different. And if we were to take these results, feed them into some of the diagnostics that I was talking about on Tuesday, it would not pass those tests, because it would say that that we have 2 very different parameter estimates here. But I think what's confusing is that because this is DFA, we need to rotate the results, and when we multiply them together, they're going to give the same predictions. If these are the loadings we're talking about, the trends would have the exact same mirror image issue. So I think we've developed some kind of post hoc chain flipping to get rid of these issues and make sure that once you do the estimation, the chains will get processed in a way so that they'll meet the convergence criteria. Okay, so this is fairly simple. You don't have to worry about it, but it is just kind of a pain in dealing with DFA in this sense. If you are to run DFA and you run across problems, this is probably what's going on. Okay, so if we just to illustrate kind of an example of what this actually looks like, if we take one of the data sets we've been working with in this class, like the Harbor Seal data from Washington, it's kind of messy. Overall, the population trend is mostly increasing, except for a few of these really patchy populations. So to fit this model, again, it's fairly simple. We have a fit DFA function to actually do the fitting. We can pass in our data, again, just like we would with MARS, and then just specify the number of trends here that we want to fit. So that fit object, as I said on Tuesday, is this, it's this stand fit object, and we can do all kinds of things like apply the tidy or any of the functions that come with stand to that object to extract any of the parameters that we want to look at. Okay, but because that's kind of a pain, I think we've also included some plots to make the kind of visualization of output, more straightforward. So this plot fitted function is just it's similar to what we have in kind of the MARS package, but essentially it's just generating estimates of the posterior means, posterior 95% credible intervals as the ribbon, in addition to the data. So that's something that you can get out fairly easily. Okay, so that's kind of what, in a nutshell, what the standard DFA looks like in the Bayesian setting. But I think that I really wanted to highlight 2 or 3 of the extensions that make it much maybe more interesting or flexible from conventional DFA. And so the first one is just more of a data processing thing. And so this is in DFA, or in MARS, when we usually use MARS, we pass in our essentially a data matrix that is time series on the rows and time on the column, and that's great for most data sets. But there are cases where we might have multiple observations in a single year of a single time series. And so in MARS, it is possible to fit these kinds of models in MARS, but it's not. It involves actually going in and manipulating the loadings matrix, the Z, because the default is going to assume that every time series is its own thing. And so if you wanted to do that kind of model, you can go in and make the loading shared between time series, but it's just a little bit cumbersome. So in this case, one of the other things we can do is take our DFA model, and instead of feeding in the data in that kind of data matrix form, we can pass in the data in kind of just a long format data frame, which will be a little bit less efficient, but also let us include multiple observations in each time step for each different time series. So in this case, there's clusters here of like the pink points that are clustering together, where we have 2 surveys together that both occurred in a time step 10, for example. Okay, so that's kind of the data processing thing. The second thing I wanted to talk about that's also kind of an interesting extension is the ability to model extremes. And so there's a lot of work that's been done on this in ecology, and there's different ways to think about including extreme events in time series models. I am including them here, thinking about primarily temporal extremes. And so in a standard autoregressive or state-space model, we have kind of our state model is this X, and the deviations in each time step are normally distributed. But there's really no reason why those fluctuations have to be normal. In this case, one of the obvious extensions is to make them something like a student t distribution. And so the student t distribution is also has kind of a mean, which we're going to assume to be 0. It also has a standard deviation, which is q, and that's analogous to the q in the normal distribution. But the third parameter is this nu, or the kind of the shape parameter. And well, I'll show some examples of what that shape parameter actually means. But so what this might look like in practice is if we have population counts through time of 2 different populations. In most cases, these deviations might look to be normal, but there are, if you focus on, for example, the blue population 2, there's this deviation kind of, I guess, at time point 15 that's very large and negative. The red population is also experiencing a series of fairly negative deviations. And so those might be better captured with, for example, with the t distribution as opposed to a normal. Okay, so as an example, so this is real data. This is real data for coho salmon. And so these are the lengths. This is the average lengths of coho salmon that are caught in coastal salmon fisheries off the coast of Oregon and Washington. And the x-axis here is just the year that the fish was recovered. This goes back to 2017. And the y-axis here is average length. This time series these time series are noisy to begin with. The average length fluctuates quite a bit, both because of kind of just the natural variability, but also just because of sampling error and the fraction, the actual numbers of fish that are sampled in any year, et cetera. I've stratified this by 4 different kinds of fisheries, and so we have some larger commercial ocean troll fisheries in green. The other ones are different flavors of sport fisheries, so there's ocean sport and charter and private sport vessels. So if you squint at these data, I think that overall, as I said, they're very noisy. There are certainly some deviations, in early 80s, late 90s maybe, where multiple populations appear to be experiencing pretty large deviations at the same time. And so this might be a good example of a situation where we might want to try to fit these kinds of DFA models to that actually include those extreme events. Okay, so this data set is up with the lecture notes for this class, and it came from RMIS, which is just a public database of coded wire tagged salmon. To actually put it into our model in kind of a long format, we need to rename a few of the variables, which is kind of what this line's doing. But after that, we can basically specify the format of the data as being in this long format, and then turn this estimate nu, which is the degrees of freedom in the t distribution. We'll just turn that on or set it to true to turn that on. Before we were just estimating things as normal. Okay, so you can run the code, fit the model, and verify that this is kind of what you get out of it. This is the posterior distribution of that new parameter, or that degrees of freedom. And so the mean here is about 20, and the median is like 16, which is what the black line represents. If we were to take a statistic like a posterior mode or something, it would be even smaller, probably less than 10. And so I think these distributions typically have long tails like that, so that's fine. Mostly what we're concerned about though are what these values are and how those might be how those might compare to like a normal distribution. So just thinking about the tails of the t distribution. When nu is large, and so large here is conventionally like 30, then the student t distribution will behave very similarly to the normal distribution and give you essentially the same results. When nu is small, that's greater evidence for having these long tails corresponding to negative, or not necessarily negative, but kind of extreme deviations. And so in our case, we were seeing, nu was something like maybe 15 to 20, depending if we're using the median or the mode, or I'm sorry, the mean or the median. And what that really would be interpreted as is maybe there's some weak evidence for extreme events, but it's not giving us estimates of nu that are very small in the range of 4 or 5. And I think that's, at least in my experience, fitting these kinds of models, finding evidence for very, very small values of nu is really hard to find. I think that's partly because a lot of the data we work with in fisheries and ecology are kind of corrupted by observation error and sampling errors, and they typically are noisy. So the t distribution might be better suited, or finding those really extreme events might be better suited for cases where observation error is really small. The other thing I'll say about this too is that I think the t distribution and the normal are both symmetric, and so if we were interested in modeling not just extreme events, but maybe more realistic extremes in biology, folks have used kind of asymmetric t distributions to model that sort of thing. And what that would represent would be situations where your your tail corresponding to negative events is much longer than the tail corresponding to positive ones. And that kind of makes sense. I think if we're working on fish populations, for example, many different populations or species could experience really negative events, or die-offs or effects of fishing, et cetera, in a year, and be depleted in a more extreme way than they would basically have positive events. That's probably more true for people who are working with data from birds or mammals, which tend to grow slower. But there's a lot of different flexibility that we could include here beyond just the regular t. Okay. So the next extension that we want to talk about is actually motivated by one of the student projects the last time we taught this class. And so the issue here is that our sampling through time might not be continuous in the way that we want to have a kind of a nice well-formed data matrix to pass into Mars. Maybe we have samples that are very sporadic in time and they're clustered. And so in this case, most years don't actually have samples, but the years that do have typically more than one. And so so as I said before, we could take this data, format it in a way that we can fit it in Mars very easily. The challenge here, though, is that when we fit any autoregressive models to these data, as I was talking about on Tuesday, we get kind of these ballooning credible intervals or ballooning uncertainty in between data points. So the further we step away from data, the more uncertain our models are, and then we start making very imprecise predictions. So that was kind of the root of this. The application is Megan Federn is a PhD student, and she's working with she has data from harbor seals, and this is isotopic data that's been collected through time. These seals were all collected from museum collections, and so the museum collections are pretty sporadic in time. There's also complicated rules about when you can and can't kill seals, and so that affects when seals are collected. And so so once she patched her data together, she had a lot of data points like this, but it's very clumped and irregular. So I think we started her for her class project fitting kind of regular DFA, and then we started noticing these problems where in between data points we're getting pretty imprecise predictions, lots of uncertainty, and it was difficult to infer what the actual loadings were for different time series. Okay, so so kind of one alternative approach that we started talking about was instead of, the autoregressive model in a DFA is great, but there's no reason why we need to be constrained to just using that as the underlying process model. And so one alternative here was to use something that's more smooth. So here, splines and Gaussian process models to really model those smooth trends. If you've worked with GAMs before, this is similar to what a GAM is doing. And so you can think about modeling the latent trend instead of being this random walk. We're going to model it as kind of this smooth function, and the smooth function can be as smooth or as wiggly as we want it to be. It's something we have to specify a priori, but it's something we can also use model selection to evaluate different amounts of wiggliness and which might fit the data best. So so what is a Gaussian process model? So as I said before, normal DFA, we're interested in modeling kind of this latent process, the x's, which are interpreted as our trends. But in a Gaussian process, we don't do that. What we instead do is model the covariance between those states or those x's. And you might be asking, well, if you have a long time series of 100 observations, thinking about the covariance between 100 data points is all of a sudden very, very complicated, because your covariance matrix is 100 by 100, and that's true. It's got tons of parameters, way more than we could actually estimate if we were to include all of those as like free parameters in a model, for example. So I'm going to ignore the splines for now. What the Gaussian process does is it just takes each element of that covariance matrix and it models it as a function. And sometimes these are called kernels or covariance functions, but there's a whole range of flexible families, the exponential, the squared exponential or Gaussian, the Matern, etc. And what we can do is model these covariance, or use these covariance functions to take what would ordinarily be a lot of parameters. And so in a giant matrix of 100 by 100, you have thousands of parameters. Instead, we can condense all of that to estimating 2 or 3 parameters that describe all of those covariances as just as a function of how far apart 2 points are in space, or for time series data, how far apart 2 observations are in time. So so it makes a complicated model with thousands of parameters something that's reducible to just a handful of parameters. Okay, so this is sort of what this might look like in practice. So if we were to take this giant covariance matrix sigma and look at, say, the covariance between observations at time t and time t plus 3, we could have some function like this, which is just the Gaussian covariance function. And the numerator here is just essentially the difference, or the distance in time between these 2 points. And so this is the observation at time t and the observation at time t plus 3. So that is something that is data. We know how far apart each data point is in time. Then we have basically only 2 parameters that control what that covariance is. And so we have this first parameter, this sigma squared, which is just the variability, and that controls how large or small those values are. And then the second parameter is this this tau, and tau controls essentially how fast the covariance between 2 points decays as a function of distance. And so when you can do this in practice, you can see that you can make 2 points that are separated by a time step or 2, very correlated or very uncorrelated, depending on how you estimate tau. And so so those are really the only 2 parameters that we need to estimate in this kind of framework. We can do this in a very flexible way, so that if we think about applying the kind of the Gaussian process model to underlying DFA trends, in a kind of the default assumption is going to be that each trend has its own. Each trend has the same covariance function, and so that basically what that means is that the smoothness. I was showing different smooths for 3 different time series a couple slides ago. think about each of those smooths is going to be the same. The degree of wiggliness is going to be the same for each of the underlying trends. But to make this more flexible, you could also have situations where maybe one trend represents some high frequency process that's very variable and wiggly, while another trend maybe represents more of a decadal, really very smooth process. And so in those kinds of situations, you might want to have two different amounts of wiggliness between each of those trends. Okay, so to actually implement this with kind of the code we put together, you can just change there's an argument for the trend model. So you can just change the trend model, which is defaults to the conventional DFA or autoregressive model, and just change this to a GP, which stands for Gaussian process. It's very easy to estimate that and compare that to our conventional models. I'm not going to get into that here, but we can play with that in lab if folks are interested. Okay, another extension is that just like that last example I showed, that we don't necessarily need to be constrained with estimating the underlying trend process as being an autoregressive one. Similarly, if we're working on thinking about the constraints on the loadings matrix in a regular DFA has a bunch of constraints for identifiability. And so this is normally what a loadings matrix would look like, where we kind of have to zero out these upper elements. And so this is true. You have to do this whether you're doing a maximum likelihood model or a Bayesian model. It's just you're kind of limited by these constraints. But there's no reason why this needs to be the only kind of constraint that you could apply to this type of loadings matrix. And so for another student project was interested in thinking about time series or the trends in the time series and their relationship as a kind of more of a true conventional mixture. And so this just represents kind of an alternative constraint that we can put on that loadings matrix. In this case, I'm talking about a mixture in the sense that each of the time series can be expressed as a perfect mixture of three underlying. In this case, we're observing 5 time series, and there's 3 underlying trends in this model. Each of these elements represents the proportion that each of those underlying trends contributes to the time series that we observe. So each of these rows has to sum to 1, because this is on a simplex. And so I think this is a different way to deal with the loadings. I think that so I think it's powerful. I've done a little bit of simulation testing, and it seems like it works. I haven't actually applied this to things in practice, and so I think there's any number of extensions that this could be used for, but I think it probably depends on the exact kind of question that you're interested in. So to fit this model, you can change we have an argument that lets us free up that Z model and change that to a proportion constraint instead of the conventional one. The situation where this was useful, or where the person was interested in doing this was more for an environmental monitoring. They had essentially contaminant data, and so you could work with data like that, or maybe stream temperature data, or stable isotope data, or situations where you think that the kind of proportional constraint would be applicable. But that's not going to be true for most of the time series models that we're working with in this class. All right. Okay, so the last section that I'm going to be kind of going through for this lecture is going to be kind of blasting through kind of what the stand models look like, so that when we start playing with them in lab, or if you're digging around on the website, that folks will kind of have a very high level understanding of what's going on. I think that that unfortunately there's a number of folks in this class who are well-versed in Stan to begin with, or are using it for their final projects, and that's fabulous. This is mostly just a primer for people who have never used it before. So the scripts in Stan are essentially text files. You can create them very easily through RStudio, and they start with kind of this upper block, which is our data block. And we can include a number of different kinds of data types in here. We can include integers, real numbers, which are just essentially scalars. We can include vectors of integers. We can include matrices, and each of these can be dimensioned by integer quantities that we have to pass in. And so there's a ton of examples and discussion about different data types and what you can actually do with those different data types in the Stan manual, which I talked about on Tuesday, but I just have linked to it here again. I'm not going to get into the weeds about data. I think just be aware that that if you get a weird error or are trying to figure out what's going on, or why your binomial model doesn't like the vector y that you passed in, it's probably because you passed in a vector of real numbers when it should have been a vector of integers, for example. Okay, so the second block that is entirely optional in these kinds of models is what's known as a transform data block. And so this is just used for calculating derived quantities based on your real data. And this is often useful in situations if you're working with data and you need to use like a multivariate normal distribution and dimension that, change the dimension of that multivariate normal based on some other argument in your data. You would need to create a vector of zeros at some place, at some point, just to include in the mean for that multivariate normal distribution. So this would be a case where you would include that vector of zeros in your transform data block. Again, entirely optional. Most of the code that we write doesn't actually include this. Okay, so one of the blocks that actually is absolutely mandatory is including this parameters block. And so the parameters block, like the data block, is typed, and so it's you can specify real parameters or vectors of parameters or matrices of parameters. Stan does not let us estimate integer parameters the way that JAGs might let us do, and so I think we can't have categorical type variables. Everything has to be real or vectors. We can also put hard bounds on these different parameters. And so in this case, if we're estimating a time series model and have an observation and process error, we know that those values cannot be 0, and so we can specify lower bounds on each of them. I think we can also specify upper bounds, but for most cases we don't actually need to use that. Okay, so that's kind of what our parameters block looks like. Then we have an optional transform parameters block. These are derived things that are generated from the things that we are declaring to be parameters. And remember, the parameters are the things that we're going to have to put priors on. And so we don't need to put priors on things in this transform parameters block. In this case, I just wanted to include an example for what the transform parameters block might look like for a state-space time series model. We have, as before, we had our observation and our process variances that we estimated. Our transform parameters block is going to include a vector of predictions. It's going to include, it's going to set the prediction for the first time step equal to the initial state, which we are estimating as a parameter as we would in MARSS. And then we just have a loop where, at each time step, we say that the predicted population size at that time step is the predicted population size one time step before times some density dependence or autoregressive 1 parameter phi times our our process error deviation. Okay. And then finally, I guess second to last, another block that we have to include is kind of our model block, and this includes all of the parameters that we are specifying along with the priors on those parameters. And then we have to include our likelihood or our data model. And so in this case, this is our prior for our initial state. We have a prior for our autoregressive parameter. We have priors for both our process and observation errors. This kind of student T prior with a degrees of freedom of 3 and a standard deviation of 2 is sort of one of the accepted defaults in kind of the STAN model for a weakly informative prior and a variance parameter. Our process deviations are going to be normally distributed. And finally, these last 3 lines are the likelihood of our data given our predictions. And so we can also vectorize this to make this a little bit faster, but just to make this clear, we're assuming each data point is normally distributed with some observation error variance. Okay. Okay, so last, a lot of the code that we've developed for this class also includes this last block, which is kind of the block of generated quantities. This is useful for doing things once after you do all the estimation for the model. And so I think this is a case where if we have some desire to do model selection or comparison between models, we can just include the log likelihood at the end of that block to do things like calculate leave one out cross validation, and we'll talk about that more next week with some other examples. But that's why you'll see kind of this block popping up at the end of the code. Okay, so just finally before we wrap up, the example I just kind of wanted to walk through that's fairly tractable is doing this in practice and showing how we could take one of the scripts we've written for the class and tweak it slightly to or modify it to include extreme events. And so in this case, we've developed a model in that ATSA package that I talked about on Tuesday. That's a state-space random walk model. It doesn't have drift, and it assumes that the deviations at each time step, our process error deviations, are normally distributed. And I just want to modify that so that thinking about extreme events, instead of making those process deviations normal, what if we change those to be student T? And so the only real change here, as I said before, both of these distributions, whether the distribution is normal or student T, they both have a variance parameter, and so that the meaning of that doesn't really change. The only thing we're really adding is including this new parameter, this shape for the student T. And so that's really the only parameter that we have to make or to change to the model. As a real world application, hot off the press, I wanted to take the daily closing stock price of GameStop, which has been in the news lately. And so this just kind of blew up over the last couple months, going from like $4 a share to $350 a share. These are the daily prices going back to January 1st of this year. And you can see that if we, I think that if you were to model GameStop price last year, there'd probably be very little evidence for using a student T distribution because it was probably very flat, or I mean, it probably was declining and probably very slowly and not fluctuating a lot with these extreme events. Then all of a sudden, thanks to Reddit, things started really blowing up at the end of January, and we get these really huge swings that probably aren't well characterized by the variability that was going on before this. So if you want to play with it, the file that I've included for this class, or as part of this lecture, has the stock price going back like 5 years, and you could explore that. But for this application, I just wanted to use the daily price for the last 2 months, essentially. I should also say that there's all kinds of financial models that deal with these kinds of things better in thinking about not just letting the variability be distributed with the T distribution, but letting the variability change through time. And so those are a whole different class of models that we could also apply here. Okay, so to do this in RStudio, it's super easy to generate new STAN files. You can just do this from the file manual. If you wanted to build this from scratch, but we're not going to do that. We're just going to take one of the files that we've already written for this class, which is just this SSAR stand file that's in our repo. And I'm only going to do make 2 real changes to that. The first is going to be, just as I said before, if we want to better capture these extreme deviations, we have to change our normal distribution to be a student t. And then the second is that to make that happen, we need to estimate this new parameter, which is the degrees of freedom of that t distribution. So the new this new is constrained in 2 ways. It has to be positive and it has to be greater than 2. So if it's less than 2 and positive, it's the variance is kind of undefined, but we want this to be greater than 2 and positive. So the thing we're going to add to our parameters block of that model is just add this parameter. We're going to call it new and specify the lower bound as 2, so it doesn't wander off into that weird space. And then we're going to tweak the model to include a prior for this. And so the prior here is going to be we're going to put a student t prior on the student t degrees of freedom. And we're going to say the mean is 2 and the degrees of freedom of that is 3. And then finally, we're changing what we had been modeling those process deviations as normally distributed. Here, they're going to become student t deviations, but otherwise everything will behave exactly the same. Okay, so then all we have to do is fit this model. And so I think the model file that I created is is in the folder for the lecture. But this is essentially the only script that you would need in R to actually run that. We have to create a list of data containing kind of what that response was. There's a few, if we're modeling daily prices, it's a little bit hard because we don't have daily prices, for example, on holidays or weekends, and so that we have these uneven gaps in our data, and so we just have to do some kind of indexing essentially to identify where we actually have data and where we don't. And that's another reason why this is a state space model, is that we're trying to infer what those, what the stock price of GameStop would have been on, say, 2 weeks ago on MLK Day, when the stock market was closed. We can estimate what the price would have been had it been open. So we fit our model, and that's, essentially everything works great. We can pull out our new parameter and look at kind of the support for extreme events. In this case, in our last example, I was showing that the thinking about the deviations in coho salmon body sizes over time, we were getting new estimates that were in the range of 15 was the median, I think. Here though, we saw some really wild fluctuations. And the new parameter here is constrained. It's basically slamming into 2, which is kind of the lower bound. So much stronger evidence here for those extreme events, because we get this. You look at the tail here now. A large value of the parameter estimate here would be 6, which is also very extreme. And so I think this would be very strong support for including those deviations as a student t process rather than a normal one. Okay, so that's kind of the extent of the script stuff I wanted to kind of go through for lecture today. Do folks have any questions about that kind of stuff?